So let me write down quickly. Haven't even checked. Well, how's the glare? Yeah, the glare is okay. So the equations that we learned. So when it comes to, we should put them here and save them. So to calculate the maximum shear stress when you twist a cylindrical shaft, either solid or tubular. So the equations used are torque times C divided by polar section modulus. And if you take these two together, this is J divided by C, you have that alternative equation over torque over polar section modulus. Okay, area moment of polar moment of inertia, J. And then to angle of twist in radians, it was T times L over was J and G. So torque, length of the full length of, or the length between which you measure the relative rotation, it could be. And then polar moment of inertia and shear modulus. And shear modulus is it's listed in several places in the book. I have this written down here. So yeah, for if it's a pipe or tubing, you would go to appendix. If it's a shape that you need area properties is appendix 1, and then for modulus of elasticity in shear, that's page 239. 239. And then if not, you can use an equation on page 82, which says G modulus of elasticity in shear can be calculated using modulus of elasticity in tension at the Young modulus, and then you divide it by 2 and 1 plus Poisson ratio. And Poisson ratio have, like for most steel, is the same, 0.3. So this is a less, or it varies less, the Poisson ratio than other properties. Okay, and this was again an equation on page 82 on chapter 1. Okay, if you want tau as function of radius, then you just say T times C will be T max, and then multiply by so to be function of, actually it's T over J times R. T over J times R. So if you have a shaft, including tubular, so it can mix material, okay, and you have like a radius R, you can evaluate it's not the maximum is always going to be or shear stress going to be maximum on the outer skin, but if it's the tubular member, it might be an interest in finding the shear stress to the inside or elsewhere in case of a, I don't know, repair or something. Okay, so these are the, as for the equations that we'll be using over and over, and you'll see we're going to make use of them in the future in design machine elements. And I'm not repeating the area or polar moment of inertia equations because it's appendix 1 where we have them, and the formula for direct shear, you just divide. It could be double shear, Pinion double shear, but in essence, you take the force that shears the member and you divide that by the area, gets you the direct shear stress. Okay. Let's see. So yeah, I think I have the equation. The equation 4.9 in the book is listed at tau is tau max times R over C. So in the book you see it, tau max, which comes from here, times R over C, but it gets you to where you see here. Okay. So I said let's go or emphasize
from this chapter 4, the problems first, where we have torsion shear stresses. I'm beginning with problem 41. And yeah, that's an easy one. Problem 41. Compute a torsional shear stress that would be produced in a solid circular shaft having a diameter of 20 millimeters when subject to a torque of 280 Newton meters.
Okay, so problem is for 41, and we have a torque of 280 Newton meters, and then the shaft diameter D is 20 millimeters. Okay, so the equations are to the left. Can you give it a shot before I write it on the board, the solution? So we're interested in tau max. Anybody? Okay, so the equation to use is right here. What is going to be C? We have T. What is C? Yeah, so you said radius C is going to be D over 2, 10 millimeters. That is 10 millimeters. When applying this equation, using millimeter power 4 in millimeters or millimeter power 3, the torque should be in Newton millimeters, remember? Because if you use all millimeters and newtons, you get megapascal. So we'll get tau in megapascal. So this will actually be used as 280 times 10 to power 3 Newton millimeters. Okay, this is the value that we'll be using in the formula. Okay, and then we can go with this one or use the first of the version of this equation. So J, it's in the book, of course, but I said for or basic geometries, we go to Appendix 1, Properties of Area. All right, and so I'm on page 552, and the first shape, it's circle or a solid disk next to a hollow circle. And we have for J pi diameter power 4 over 32. So pi diameter of power 4 over 32. Okay, so we can calculate polar moment of inertia in millimeters at power 4. So pi times there will be 20 power 4 over 32, and we get so I said at power 4 times pi over 32, and this is equal to one, and I need to put it in the memory, 15707.96. Let me make this 8. It will be millimeters at power 4. Okay, so now I can calculate tau max using this equation. So the torque 280 times 10 to negative to power 3, not negative, times 10 over, still in the memory, 15708. The multiplication. So I take 1 inverse, shift inverse, and then times 280 exponent 3 times 10 equals, and this is 178.3 megapascals. Okay.
Was it clear? Okay.
I'm sorry, real quick. J was that in the chapter or
It's in the chapter, but I encourage you to instead use the first of the appendix, which is on page 753, and you have properties of area, appendix 1, and there's also polar section modulus. So if you want to use this equation instead, you use pi diameter power 3 over 16. All right, you found it? Okay. So yeah, I'll maybe I should even put it on. So page was 753. 753. And likewise for this one. Okay. Yeah, so we have a stress. We don't know the properties of the material that the shaft is made of. But if it was one given, and we can add to this. So let's assume I'm making up quickly a material. So carbon and alloy steel, or maybe, no, let's do this. Let's select the material that is proper for this application. Let's assume it's a steady torque for which the design factor would be, and to get that, it's page 709, which is a summary of design factors. So go to page 790 and it says design shear stress for direct shear and torsional shear stresses. These are for ductile material. So static loading at that steady torque, design factor is going to be, is usually 2. Okay, for others would be more than 2, and you also need to make sure you use the right reference property. So select the material. And this will be carbon or steel material. So design factor is n equal 2. Assume static loading. Static loading could be, like driving a fan would be the best example to describe static loading. There are transients, and you might pick, or the torque might pick as you start up and you accelerate. You need to work against inertia, but that may happen only on occasions if it's an industrial fan that runs 24/7 or to circulate the air in a underground on a subway. Okay, so design factor of 2, and we need the yield strength. So on the same section of the table, we use design shear stress. So this is going to be our design shear stress, tau d. And the equation, so tau d, is now in terms of yield strength, which is approximated as half of the yield strength in shear, as the long equation right above where it says tau d equals SYS, yield strength in shear over N, or 0.5 SY over N. Okay, so I'm copying the equation tau d equals SY over 4, coming from 0.5 times N. So it's, over 4. Okay, so we need, we have the design stress. We decide upon the design factor, and we want to find SY. So that is yield strength in tension. Minimum required, and that's going to be 4 times tau d. So it will be 4 from here times tau d, 178.3. Okay, and what does that equal to? Went to 0. So 178.3 times 4 equals, so this is 713.2 megapascals. So what do we do with this number? Now, again, we need to select the material and have to be that is a steel material. So with this, we go to the appendix on carbon and alloy steels, not structure steels. So carbon alloy steel, that's page 782. And we looked on the column for SY, and well, let's see. As you go down, you start seeing the first one, the first carbon steel, 1080 oil quench and temper 700. Shall we go with that one? Those are high carbon steel. They are steels used for tools, for chisels, for files. So no, let's forget about that. There is the 1141 oil quench and tempered 700. Okay, that's an alloy medium carbon steel with a yield strength of 1,186. There's also the one below, oil quench and temper 900 with 889. So we can use SAE 1141 oil quench and temper 900. So use from here, use SAE, what was it, 1141 oil quench and tempered 900. 1141 OQT. Do you understand what we're doing here? Yeah. Okay, there are other candidates. So the 4140, and it might be a cost reason to where you choose one or the other. In terms of, for us, anything like in the 800 range is fine. Maybe read more about the difference between oil quench and temper 900 and 700. So 700 might be a more rapid cooling, and not all parts may end up that strong as listed there or something. More variability in the process. But yeah, this was it. At the back of the chapter 4, there are problems where it says choose a material. And this is problem 49. Other questions about this? Okay, so it looks like I got it clear. So for example, problem 49 now, it shows a lawnmower. So it says shows the end of the vertical shaft of a rotary lawnmower. Compute a maximum torsional shear stress if the shaft is transmitting 7.5 horsepower to the blades when rotating at 220 RPM, and then specify suitable steel for the shaft. If you look at the figure now, you see that there's a profile key set. What does that mean? And we also have a retainer ring over a diameter. Is the diameter specified? It's missing a diameter, but there's a dimension there. However, below the blades, you don't have any torque transmitted. Does it make sense? You're still taking notes about this? Are you? Okay, you can take a picture. You can take a picture of this, and we can move to problem 40 now. No, I'm going to erase the board. Again, the projector has to be on because the blank screen thing is not working. Oh, it does. Miracle. But maybe it's too dark now. What was the time when you could turn on the well, maybe we'll go back to really this one maybe. Oh yeah. Okay. Yeah, it was a sliding okay. So we can use the sliding boards. And for problem 49 now, we need to calculate the torque given the power and the RPM, and then we need to account for the, there are two places where there's an increase in stress. Can you tell them? So there's one at the step. There's a transition, and I put here 0.75 inches going from 125. Do you have anything in your book in terms the minor diameter where the groove is? In my book is missing, but I put 0.75.
So 49. And so we have, let's draw just the shaft, forget about the actual blade. So we have the axis of symmetry, and then we have the step with the fillet, and then it goes to a groove, and then it's the end of the shaft with a chamfer. Usually you want to have that chamfer. And then there's the profile key. Okay, we have R is the fillet radius of 0.05 inches. We have the major diameter D, and this is 125. And I made this 75, although it might be, so minor diameter is 0.75 inches. Might be too severe transition, but it's what I chose. Okay, so we can tell right away the stress concentrative factor at the key for torsion. It's in the book, I think elsewhere also in the book that is in the chapter. So for profile key set, it ends abruptly, not the sled runner. For sled runner is 1.6, this is 2.0, okay? And we're going to also look up stress concentration factor in torsion for a step shaft with a fillet radius, assuming these two diameters. The groove is below the blade and it's not loaded in torsion. So it's a good location for a retainer ring because there's no torque there. But we need to calculate the torque that's loading the shaft and resisted, of course, here at the at the blade. So to calculate the torque, we are using the power equation. I have it added, the advantage of using the paper book, but it's in the text. So power in horsepower, we have that equation. It's torque times RPM over 6325 it is? 6325. So from here we can solve for torque. Torque is going to be 63,025 times power in horsepower divided by RPM. All right, so 63025 times the power was 7.5. Yes, 7.5. Yes, over 2200. I'm listening.
I was just wondering where that's 4 times angular velocity, and where did you pull the constant from?
This is, I mean, the equation really, it's in the chapter. I have it written with the conversion factors, but the place in this book where you can find it is on page, I'll tell you in just a second. Come on, page. It's equation 4.6, page 213. So page 213. Formula for power and torque. If it's in metric, that's easy. So in metric, torque times omega is power. Torque in Newton meters, radians per second. Power, it will be in watt. So Newton meters, radians per second, and power in watts. Right? Okay, so we can now calculate the torque, and it's going to be, we said 63025 times 7.5 over 2200. So it's 214.85. I can easily say 215 pound foot of Yeah, we need to make sure the units match. So I think it's pound-foot. Was it problem page 213? I said. So pound. No, it's pound-inch. Pound-inch on pound-foot. So pound-inch. And so yeah, we have a torque. Next would be to calculate or find, this one is clear, stress concentration factor here at the step. And for that, we go to the right appendix. I think we've been there before. And no, we analyzed one with okay, so one with a hole that had a common chart for axial torsion and bending. So for stress concentration factor of a step shaft in torsion, you go to page 798. So 798. And there's a figure, there's a chart. So we have to calculate R over D, fillet radius of a minor diameter, and then we read coefficient of stress concentrator on the vertical axis, and we need to choose the closest, or maybe it's readily available curve, D over D. So we have 125 over 0.75 for the curve, 125 over 1.25 over 0.75. You haven't confirmed. Is this visible on your PDFs? I need to check if they have it in the new book. Maybe they wanted.
Yeah. Is it like blank out? Yeah. I can send you.
So does it show that diameter?
Yeah.
Which is?
It shows the whole graph.
And is it indeed 0.75?
No, it doesn't show that problem. I was talking about the graph on page.
Oh, this one with the. Oh, I think that. So you have some PDF users. You have issues with the appendix.
No, the appendix is okay. Just this problem itself, where the diameter 0.75 is not in there.
It's just a dimension line, but doesn't have a diameter. Yeah, right. Well, I made it up. It's handwritten in my book.
Okay.
All right. So blame it on me. It's a bit severe step. Usually want to have the difference less. The ratio between major diameter and minor diameter 1.667, and it's a curve that is readily available. I think that was the reason why I chose it that way. So we have the curve that says D over D is 1.67, and then this ratio now is 0.05 over D. That's 0.75. So I said 0.05 over 0.75. This is 0.067, and it will be, I have 0.5 and 0.1. So in between them is 0.75, or rather, I'm sorry. So we said 6.5. So we have, it goes every, what is the spacing? 1, 2, 3, 4, 5. Okay, so it goes every 0.01. So the next line is 0.06, 0.07. It's closer to the second line from 0.05. We move up, and I would say is 1.55. You understand? So it might give or take is, we said 1.55 kT, all right? Okay, so we've got the stress concentration factor, which happens to be less than for the key. So tau max now, again, this is not a sliding board. I'll switch to sliding board. So tau max, or rather maybe say design stress, tau D, design shear stress, is going to be the biggest of the two, the stress concentration factor, and that's clearly going to be the one due to the key.
So KT at key, and then times.
And if you look it's still on appendix on page 798, there's a format that gets you the nominal and the tau max. We use tau max because it's on the outside. Anyway, so nominal would be T times pi, diameter power 3 over 16. We calculate with the minor diameter. So torque, we've got it, over, this is polar section modulus, pi diameter power 3 over, but the folder small diameter. So pi diameter, minor diameter power 3 over 16. Okay, so KT we said 2.0, torque, the one that we calculated, and then the diameter 0.75 inches. All right, so let's see. 2 times 215 pound-inch over pi times 16 over 0.75 at power 3 equals. And I've got 5,191 psi, or 5.1.2 ksi. 2 ksi. And then it says, so all clear so far? Again, we've got 2 stress concentration factors. The second one was bigger. We used it at the profile key set. And now we need to, what? Select the material. We've been here before. Question is it's a mower. I mow my grass the other day and forgot about a steel rod that I put it to prevent a hose from, when watering the garden, to go over some plants. And I mow the tip of it. So, by the way, when I bought it, the warranty was, I think, 1 year for personal use and 90 days for commercial use. The warranty. So it has something to do with, the more intense, and it should be sold in California. I'm still using I haven't switched to a Tesla mower yet. What was it, 5 So what do you think it's this? It's repeated loads or static loads, or it might be something in between. Mowers, you can get overloaded. So going with just 2 might be a little bit on the limit, but you do test and you can correct. So we can assume, take the common value n equals 2 design factor, with the caveat that I say it might go on the overloading side. So for that, with that we can calculate the SY. We had a formula on the board. Minimum required. Same as for the previous problem. So that's going to be what? Tau D divided by, multiplied by 4. Tau D times 4. Tau D times 4. Again, with a stress concentration factor of 2. And it's still okay. So this is a small value over what carbon seals can do. So times 4 now, and then over 1 exponent 3 to get in KSI. So it'll be 20.76, 21 KSI. Yield strength minimum required for the material to use it for this mower shaft, which is actually the crankshaft. The mower, the one that drives there's no gear reducer in between, or any kind of reducer. So we go back to carbon and alloy steels, and remember the slogan, use the worst good material for the job, worst being cheap. And well, there's machining required, so that's another. It may go against being the cheapest possible. And we might have to harden it because there are additional stresses here, as the key. We haven't discussed this, but it might, induced bearing stresses. So let's go with medium carbon, plain carbon steel. And we can go with one that is 1040 Cauldron, for example, easily. It's 97 KSI. So from here on, you start thinking at other implications like availability and machinability. So if it's Cauldron, it's easy to machine. You need to cut the key. So we can use we say SAE 1041. I'm sorry. No, I'm sorry. 1040 Cauldron. 1040 Cauldron. If it's Cauldron, it's easy to machine because it's work hardened. Okay. All right.
We were doing the math real quick, assuming there would be a lot of impacts like hitting your steel rod.
Well, we're still way away. I mean, even if you go with the highest of the stress rise or at the design factor, 62. This is still okay, even for that instance. Okay. I mean, the only damage that I did by mowing through that steel rod, well, it was a rod, and I put a piece of hose, and it was green, and grass was green in that area, and didn't see it. So, and it survived. It damaged the mower blade. Oh, you mowed through steel rods in the past as well? Okay, it happens. All right, problem 50 is on the list. If you look at it, so we have a stepped shaft, and it says there's a hole there, and we need to compute the stress for a torque given. And it says determine a large hole that could be drilled the shaft and still maintain the stress near the hole at or below that at the step. Okay, so it's a bit of, because you need to work with the chart, there's a bit of try and error. Actually, no, you solve for the required KT at the hole. And you read the chart in reverse now. So you go with the required KT, and you go in reverse, and you can calculate the diameter of the hole. I'm pointing to the wrong graph, but do you understand? This is for problem 50. And the problem 50 is designed to where it says what would be the maximum diameter of the hole, which is noted A now, that limits the torque due to stress riser of the hole, same as for the step of the shaft. And there you go in reverse. So you calculate the maximum allowable stress concentration factor due to the hole. You go and read the ratio between the hole diameter and the shaft, and you report the hole diameter. Of course, it has to be rounded to the nearest size, but you round down. Does it make sense? So you've got it the maximum possible, be a fraction number, but you get with the next available drill down, not up. Okay. Other questions? Does it look like engineering?
Yeah.
Okay. I'm glad you start liking it. So, it says compute the angle of twist of the free end relative to the fixed end of the steel bar showing in figure 467. So angle of twist problem. Yeah, problem is 467. Problem 467. And we have again, this is a problem, like textbook problem, and when you see this slender, like 120 meter, or rather 1.2 meters, that's a lot of overhanging, rather slender shaft, so it has to be supported, really. You cannot keep it like it's shown, but it's a different story. So we have a torque T of 200 Newton meters. Okay, and then we have, this is fixed end, and we have the corresponding length given. One I said is 1200 millimeters. The other one is 400 millimeters. And then we have the diameters. So this one here is 40 millimeters, and the other one is 20.5. Okay, and we need to calculate the angle. So this is fixed end. You put a torque, and it's long and slender, all twist anyway, but maybe more noticeable amount. But we have two sections. So how do you go about solving this this problem? Again, you remove the load or not apply the load, and you mark a line and say you have a stationary reference. You know, I show it fixed together with this one. And then as you apply the torque, there will be a rotation in the direction of the torque by the amount theta in radians. Does it make sense? It's what it is. And we want to calculate this one. But the shaft is not continuous in diameter, has two sections. So we need to distinguish between the relative rotation between the fixed end and where the step is. There's no labeling, so you can call this A, you can call this B, like right here, and C here. Or maybe C on the invisible face of this disc that you use, or whatever it is, to pulley to apply the torque. Or maybe you wrap a cable in. Anyway, so tau at C equals tau at B plus tau between B and C. It's what it is, okay? Same as with tension. We solve problem with tension. If instead you pull the free end C, you have an stretch of portion AB, which is one thing because we have a bigger diameter, and then there's the thinner portion that will stretch, and you add the two and you calculate it to report a total displacement of point C in the direction of the force. But here's torsion. And we had the equation for torque, or the angular or twist, angle of twist in radians. So let's see what we need. We have the torque, and by the way, the torque is the same everywhere, clearly. You know, any portion of the shaft, it's subject to the same torque. And then we have the respective lengths. So this will be LAB, and this is LBC. Material is the same. Polar moment of inertia changes because we have different diameters. And then the same modulus of elasticity in shear because it's made from one single piece. So it says a steel bar. So on page 239, you have modulus of elasticity in shear for steel is 80 gigapascals. Okay. And the equation, again, the equation to use would be the one below. So theta is going to be torque times length over polar moment of inertia over modulus of elasticity in shear. Okay, so let's calculate the two. Theta B, or could be between A and B, the same thing. Why is the same? Because this end is fixed. So it's going to be the torque times length AB times would be pi, and let's call this DAB, and let's call this DBC. So pi D AB, rather 4 power 4 over 32. Okay, and tau between B and C
it's the same torque length between B and C, or length of section B and C, pi, and then diameter between B and C at power 4 over 32. Okay, so remember, torque has to be in our type of units, which is, we've seen this before, so it has to be in Newton millimeters. So we take 20, or at the 200 times 10 to the power 3 Newton millimeters. We don't like meters in this class. Let's put it this way. So we have 200 times 10 to the power 3 times length AB1200 over pi 40 to the power 3 over 32. And then the second one, same torque, 10 to 3, length is 400. Okay, and then pi, the diameter is 20 power 4 over 32. Okay, just to confirm. So where is that coming from? Have we ever stated this anywhere? Yeah, it's the equation from appendix, if you want the appendix 1. My calculator that I care a little about, it's on the floor. So yeah, to confirm, we use the formula pi diameter power 4 over 32 on appendix 1, which is page 753. Let's put some numbers on these. Anything that we can unify these equations, they differ by this piece, right? So I don't know if you, in case of an exam situation, if including, you'd think, how can I save some time? So yeah, we can calculate the common part and then take and multiply by what I encircle in blue. So 200 exponent 3 over pi times 32 equals, and I put it in the memory, and then for this one I say times 1200 over 40 at power 4 equals, this is 954.9. This is a big value, and I think we're in the formula we missed something. So it cannot be this many radians. This is like 3 turns. So we missed this. Is that correct? So we need to multiply by, in the formula, by G. And then here will occur, it has to be in megapascals, by the way. Likewise, we don't like gigapascals, so it'll be 80 times 10 to the power 3 megapascals. Okay, so I'll say 80 times 10 to the power 3 times 80 times 10 to the power 3. Okay, so I can salvage this equation, but I'm going back to what I have in the memory, and I'll just say divided by, so over 80 exponent 3 equal, and put it back in the memory, and I'll say times 1200 over 40 at power 3 equals. So this is 0.4775 radians. If I want it in degrees, I need to multiply by 180 and divide by pi equals. So it's 27.36 degrees.
Did a 40 cube, 40 to the power.
Oh, I think yes, I put it at power. So like, I can redo it. So times 1200 over 40 at power 4. Thank you. Yeah, repaying attention. This is still big. 27 degrees is a lot of twist. Okay, so it might be a more plausible number, 1194 radians, which in degrees, which we have a better sense of degrees in radians. So times
180 over pi. So this is 0.684 degrees. Okay. Let's move to this other one. What is in the memory times 400 over 20 at power 4 equals, and this is 0.06366 radians, and or in degrees times times 180 over pi equals. So this is, I got 3.6448 degrees. Is this correct? Let me try again. So what was in the memory? And then times 400 over 20 at power 4 equals. And then, yeah, times 180 over pi equals 3 points. All right. One thing we could do is not part of the problem. So yeah, thanks for not seeing. It was a mistake here. I put 3 instead of 4, power 3 instead of 4. We have some numbers. We can analyze it from the perspective of what the book recommends. So there is, for torsional deformation, there's some recommendation torsional stiffnesses. I'm on page 237, and it says recommended torsional stiffness is angle of twist per unit length. So we have general machine parts, which might be this one, and it says radians per meter or degree per inches. We have both radius and degrees. So general machine parts, it says between 6.9 and 10 to negative 4 and 6.9 10 to negative 3 radians per meter. We have essentially assuming the full length, okay, the end result. So L, we're at the theta because we never calculated this. All right, we can, we calculate them individually, but never calculated the full angle or end point C angle. So we say 0.1194 plus 0.0366. All right, so this is 0.1056 radians. Okay, so we take theta between A and C, or theta at C, all right, and divide it by the full length, LA to C. So 0.1056 radians, and I need this in meters. So in meters will be 1.6 meters. Let's see what value is this. Over 1.6 equals. And this is 0.066 radian per meter.
I got 0.0756.
When you added the two,
Yeah.
maybe I, oh, you know what I did? I added this one. Thanks. So what is the correct value?
0.056.
56 radians.
0.0756.
0.0756. 0.0756. So let's change this. Appear big.
I looked at the values there, so we are off. So 0.0756 over 1.6 meters full length. So this is 0.04725 radians per meter. Okay. And if we're to write it like fraction it, so it will be at -1, -2, -3. So it's 47.25 times 10 to -3 radians per meter. And this is less than the higher limit for general machine parts. So we are within the recommended, or is it? I said -1, -2, no, -3. So it's 47.25, and the maximum should be 6.9 times 10 to the negative 3. So too much twist. So this is way bigger than 6.9 times 10 to the negative 4 radians per meter. Is it clear what I did? There's a bit of calculation mistakes in between, but with your help, thanks, Roman, we have an answer and we can give a verdict. If this were a general machine part, we have too much torsional flexibility, too little torsional stiffness. Comments? Questions? Was it clear what I did?
Yeah, but so the end result should be in radians per meter.
No, the end results.
Degrees.
The end result should be this one, or in. Does it say whether to be in radians or degrees?
I got 4.331.
Yeah.
Converting to radians.
Okay, so I think was one that, well, if we take this one, which I think we agree it's the correct value, we can convert it to 0.0756756 times 180 over pi. This is 4.33 degrees. So it means one of them was wrong? No, I think if you add this and this, you get this one. Do you? Okay. So the answer, compute the angle of twist. It does not say whether it's degree or radians. We have a better perception of the degree than the radian. But when it comes to analyzing, is it too much twist? And assuming this is a machine part, but it does not look like one because of the stationary end, we would say that it appears to be too much twist. Okay. Other questions? Comments? Thank you. There are additional problems going along the same line. For example, stress concentrators, load is other than static or steady loading, repeated torque. And then they come, they begin non-circular sections. We need to cover those. It's 106. Let's move now to the, I said is, it's what? More in line to what we saw in earlier chapters when we discussed shear stress, direct shear stress. Essentially, you take the force that causes the shear divided by the area, and you need to maybe assess what or calculate that force and decide what the area is. Here's one problem. So problem 30. I want to go over it because you're going to see. Anybody's taking design machine elements next semester? You think so? Okay. Yeah, actually, this can stay, and I can. So you took your picture of the board. Just let me know when you take the picture, so I can. All right. So I'm lowering this, and we. That's fine. Okay, problem with a key. So we have problem 430, and in design and machine elements, we are going to discuss keys, coupling, and seals. So keys, splines, couplings, and seals. So it says a gear transmits 5,000 pound-inch of torque. So torque is 5,000 pound-inch. And then to a circular shaft having a diameter of, and now I need to draw the shaft. And there's a nice figure there. I could project it rather than exercising my drawing skills. I mean, I could. So we have the key. Let me exaggerate. I have the key, and it's sunken into the, meaning that these are invisible lines,
into the shaft. And then we have like also their figure. Okay. So it extends and yeah, let's say it ends here. It's longer than actually no, you see like so, maybe. Or maybe even, you know, we don't care where it ends, or it's bottomed. Usually it ends as a it ends like this. So we have a torque transmitted. We know the diameter of the shaft. The promise, I could do a better picture, even particularly looking at one that's already there, but it's not at the purpose. So we have the diameter of the shaft of 2.25 inches. 2.25 inches. And the key is square, and it's 0.5 inches on a side. Usually at this size, they're square, and it is. So we have this is 0.5 inches, and this one is the height is 0.5 inches. This we call it W. This is called it H. Notation from Design Machine Elements. This is an invisible line, and yeah, this is the side of the key. And we need to so material for the keys, SAE 1020 cold drawn steel. And we need to calculate the length of the key such that the design factor in shear, it's 2 based, it says based on yield in shear for the, so we have also bearing stress. To be safe in shear, and then says use a design factor. Okay, the key is made of determine the required length to be safe for the shear and bearing. Use a design factor of 2 based on yield for shear and the AISC, American Steel Construction allowable bearing stress for the same key. Okay. So we're going to have, and there's slight differences, but we're going to assume that the shearing causing force is acting like a key is inserted half into the shaft, and the other half interacts with the hub, which is not shown. Okay, so we have the shear force upon the key, like right here, F. And how do we calculate it? F, you take the torque and you divide it by the radius, the arm, which is half of the diameter. Okay, that's the shear causing force. And we can calculate. So again, 5,000 divided by half of 2.25, and that's the shearing force. I think I dropped something on the floor. Cap. So 5 exponent 3 over 2.25 times 2 equals, so this is like, what is it, Davis law theorem, 4. How many 4s? 4 4s and another 4 pounds. Okay. We need to find yield strength in tension for the for this low carbon steel. We go to the back of the book where structured steel end and where properties of steel begin. So 1020 cold drawn. 1020 cold drawn. The third was low carbon steels, plain carbon steel. So the yield strength is 440, working, we need KSI, so 64 KSI.
Yeah, percent elongation is 20, the ductile material. So 64, as expected, 64 KSI. Okay. So do we have any information about how the torque is transmitted? Well, it says to be a factor of safety of 2, so it's assumed steady loading, steady torque, right? So rather than searching from tables through the book, we go we go where mechanical properties of materials end, and we have for design shear stress for direct shear and for torsional shear stress. Now we are dealing with a direct shear, and, and for N2 design factor means this static loading. So the equation is tau d equals SY over 4. Design stress tau d, which is going to be the shear force, this one, over shear area, area shear, and I'm going to replace this, okay, equals yield strength in shear over 4. Or maybe it could have said, 0.5 yield strength in shear over the design factor. What about this? I wanted to connect it a little bit better with the text of the problem. So design factor is 2. This is an approximation of yield strength in shear. And what is the shear area now? What is the shear area? How does the key shear there? I think you handled the Woodruff keys that I brought, and I said are more valuable to me than new ones. So how's the key going to shear? The key is going to shear along this line. Okay, essentially you have the hub. Look also on the figure in the book. So you have the hub and you have the key, and they tend to rotate relative to the other due to the loading. And end result would be, if you imagine this being very soft material for the key to shear under your eyes, yeah, it's a better idea, but you bottom it. It sits all the way to the bottom. Yes. So what is the shear area? What do I write here? Yes. So it would be W times L. So it would be W times L. W times L. And we don't know W. So we have the material design factor. So we need L. That's what we need. So from here we get L minimum required. And this is going to be what? So I can go with 4. So the L is F times N over W over 0.5 SY. So F times N over W over, over W over 0.5 or over 0.5 times SY times L. Okay? So F, that Davis law firm times 2 over 0.5, or could have been a 4 there, 0.5 times yield strength in, it's 64. We need to take the PSI, so 64, 3 zeros, and then times, hold on, why do I have an L here? I solve for L. So one more time, it's this times this over this over this. So F times N over 0.5 SY over W. Okay, that was it, W. So W is, we said 0.5 inches. All right, so let's see what we get. So I could say 4.4 times 4 over 64 exponent 3 over 0.5 equals. Okay, so I've got 0.555, or could make a 6 here, inches. Okay. And this is where engineers flex their muscles, because on one hand, this is not a preferred size, firstly, and secondly, you don't want to have a key that looks like that cheese cubes you can buy at HEB. Your keys are usually longer, right? So you need to match it with the, and again, more of it in, match it with the size of the hub to get a good portion of it. Sometimes the key works as a sacrificial material. You want to go with a key that's made of aluminum. If you want that to happen, you protect the more expensive shaft and hub. But staying with the cheese cube, at least make it preferred size. So I know what you'll do. You buy, when you do shopping at HEB, you take a caliper and measure in average what's the size of those cubes. Are they, probably they're 1/2 inch. I close my eyes. I remember I was a student and a professor made a joke. There was one tall engineering guy, and he checked in at the hotel, was sent by the company with some business, and he looked at the bed and looked too small for him, a really tall guy. So went and bought a tape measure, measured the bed, calculated diagonal, and compared with his his size. So instead of checking, do I fit this bed diagonal? Okay, so I was looking for the list of preferred sizes, and we have 0.5, and then it's 0.5625. I mean, we can take 3/4 to look a bit more like a long key, but that even 3/4 on it might be too short. But let's go with 0.5625. 0.5625 inches, just because preferred size. But again, it's too short key. Preferred size. So now I have a length, and we can calculate the bearing stress. Okay. So where is bearing going to occur? Is going to occur between this face of the key set and this side, and continuing, or depending on how the torque is delivered. So contact may be made here and here, or the other way, depending on the direct between hub and key and shafting key. Do you understand what I'm saying here? Okay. But in any case, either case, the bearing stress area is going to be, so area bearing, it's going to be half of the height, 1/2 height times length of the key. Okay, and now I have a length, so we can calculate it. It's going to be 1/2 0.5 times, we said 0.5625, and these will be inches squared. All right, so 0.5 times 0.5 times 0.5625 equals. So this is 1.140625. Maybe I should put it in the memory. Too many decimal inches squared. Okay. And well, here they go into more details. So American Institute of Steel Construction, allowable bearing stresses. So let's see what the chapter says. Otherwise, you just calculate the bearing stress, sigma BD. It's occasion core is just B, sigma BD. You just take that same force that causes shear. And like I said, they differ. There will be a bigger force causing the bearing stress on the lower part than on the top part. It's how it is. But we take that like the in-between force over the bearing area bearing. Okay. And this one has to be less than the design factor divided the yield strength in tension over the design factor. And this will be for bearing. And we check it against recommendations. It's the way it is. So at the limit, all right. So what is the bearing stress? BD. Force, we have it 4.4 over the area that I put in the memory 0.625, and so take the inverse times 1,234.4 equals okay, so I have 31605 psi, and I can now calculate the limit bearing stress with a design factor of 2, or calculate the design factor. So from here, you take this, put it, we can calculate what the end bearing is. And they should be equal. If I kept the calculated length, we'll get the number that is less than 2. All right, so equals, I have this whole thing calculated, so it has to be SY, which we have, over sigma BD. BD. All right, so I have the bearing stress, and take the inverse, and then multiply by 64 exponent 3, and it gets me, as expected, 2.025 design factor. It's slightly bigger than 2 because this went a little bit bigger. Does it make sense? That's why. If you kept it the same, and with this approximation, this equality is guaranteed. For squared, if this equals this, and you do this approximation, then and you keep the calculated length for one, it provides you the same design factor for the other two. Okay, but let's see what that's. So American Institute of Steel Construction, this is like structures. So let's see what does it say. And for bearing stress, we need to go to chapter 3, and we have, let's see, what does it say about bearing stress? So it says applied load or a bearing area, and then there is a table that tells us. We passed it. So design bearing stress for aluminum, and then we have aluminum. Yes, where is it? Okay, for steel, so it says, according to American Institute of Steel Construction, reference to, I'm on page 177, this is chapter 3. The allowable bearing stress in steel for flat surfaces or on the projected area of pins in ream drills and bored holes is 0.9 times yield strength. So 0.9, what would that be as a design factor? 0.9, you take the inverse of, that's 1.11. But that will be for buildings, not for, again, I'm teaching the machine design class, and this is, we stick with 2 for both. So in terms of American Steel Construction expectation or recommendations, we are way over. Does it make sense? So again, we made reference to what page was 177. So 177, and it says sigma BD should be 0.9 yield strength in shear. Starting with shear calculation first and imposing a design factor of 2, we ended up with a much, or this type design stress, or design factor, instead of being 1.111, so versus, which is 1.9 versus, okay. Was it clear? Yeah. All right, so we did yet another problem, and as I said, the theory is once you have the force and the area, it's pretty straightforward. And with other problems too, you may say, once you know the torque and you know the solid round or tubular, you can, and maybe the stress concentration. factor there going on. Let's look at problem 416. You have other questions?
Could we just go over this problem one more time?
Over this problem one more time. Maybe because I went, wrote here and wrote above and below.
So like,
But there's the YouTube. Don't forget. But otherwise, what was unclear? I mean, I can.
yeah, so we were told to find the length.
Yes.
To be safe for shear and bearing. So the first thing we did was found the shear force.
Yes.
F, and then where did we go from there?
So once you have the shear force, you can calculate the shear stress. So I started with the shear stress because it's chapter 4 and talks about shear. Bearing stress was chapter 3. And we calculate the shear area. In the shear area, you have the square key, and it will be like this one as you close the, and where would be like a relative sliding between the two pieces of the key as you exceed its capacity. So the shear area is going to be a length which we don't know times this width. So we calculated the design stress and shear stress, given force, shear area with L unknown, and we had.
That's where you lost me. So you said that tau was equal to F over WL, but then you equaled that to.
Okay, so this has to do with you have a stress, but this is what we do as engineers. Is it too big, the stress, and how, for what? For the given material and with the recommended good practice. So we went to where all the design factors are, recommendations about design factors are the back of the book. We can go to the chapter, yes, but this is our all together. And it's where the properties end. So I'm on page 790, probably where you got lost. And we've been here before. So we have design shear stress for direct shear and for torsion shear stress. Can you see it on page 790? And you have static loading. Yeah, that was assumed. And I stated the second equation. But this is not exactly like that. In the table, it says tau d equals SY over 4. But instead, I said 0.5 SY, which is an approximation of yield strength in shear, okay, divided by design factor to make use of the design factor that was specified. Okay. Otherwise, you just say equals SY over 4. With this and this together, that is 2 making for the 4. So you calculate from this equation, you calculate the required length, minimum required length, and we got it. And we round it to the closest preferred size, but I commented it's too, even then it's too small. You don't want a key that looks like a cube, like a die, or that HB cheese. So, other than increasing it slightly, and we stuck with that preferred size value, we calculate then the bearing stress. And it's the bearing stress, I moved with a problem here on top. So how do we calculate the bearing stress? The contact area that is either between the shaft and the key or the hub and the key, that you divide it by the same force. So that's the bearing stress. So contact happens between the key and the shaft, which would be, depending on the direction of the forces delivered this way, or between the hub. So this is the bearing area between the hub and the key. And you evaluate the bearing stress by dividing the same force with the bearing area. And the bearing area is same length times half of the height, up to 0.625. I think this is the where they switch to flat keys. The smaller size keys up to 0.62 whatever, they are square. So height equals width. For larger shafts, it's wider than it's tall. Okay, so we calculate a bearing stress, and we want to limit the bearing stress. Again, I teach this machine design class where we take the same, like what is the design stress for bearing stress, or design factor, I'm sorry. You take the yield strength in tension and divide it by design factor, which happens to be also 2 for machine design. And I calculate with this formula, the bearing stress, I calculated the design factor in bearing by taking the design stress in bearing and divided by the yield strength, or the other way, yield strength divided by the bearing stress, okay? So yeah, you may have to go back to read about bearing, but I hope concept is clear. We did in a hurry. A problem was a heel, remember? It was shaped like a rectangle, half of a disc, and you put all your force on that area. You can imprint the heel into a soft material in a melted asphalt somewhere downtown, maybe. Okay, so there's no substitute to going back to the book and reading it or watching the recording again. Was it clear? Did I repeat it? Okay, fabulous. So it's 134. Let's look at the problem that requires a little bit of statics. I said I'm going to also lecture on, maybe I will. Okay, so among problems from chapter 4, and it's a recommended problem, and of course you're curious what will be tomorrow in the exam. So I'll begin by asking last moment questions. If you have, and of course there's you studying, you can send me an email and ask, I think somebody, was it you to ask about the specimen? No, maybe. Okay, so somebody sent me a question, and I responded just to the student about what was the problem there. Anyway, so yeah, if you have questions, send email to me. I'll copy everybody, and then right before class, I'll ask if you have last moment questions, and then the test will cover everything that you saw problems about from me. Okay? Yes. I love this question. Ask me 5 minutes before the exam, and I can tell you exactly. What, does it matter?
We have an hour.
Yes, but we have a second hour that we can leak into, if needed. So yeah, that depends on how you're going. If I see students that still halfway through, I'll allow extra time.
How fast do you expect us to be able to answer one question?
I'm sorry.
How fast do you expect us to be able
Well, I'm yet to see. It's the first. I saw the FE type quizzes, and there were a lot of guesses. Some were good guesses. I mean, some students scored 9 points with a lot of guessing. Good for you. You should go into, like a part-time job, poker players, or, I cannot tell you. I mean, really, it's what
That's a better question, probably. What section do you think will be most heavily? We covered most of, let's say, chapter 4, and even understand or understand what will be your primary emphasis.
I understand. Okay, so don't go with like a snow plow. I want all the problems recommended, and you're half through, and the other you haven't touched. So cover, all get a feeling of everything. There'll be time to go back to some of the recommended problems later, but don't come with material that is not covered. I'm not going to disclose to you what, sometimes students tend to ask or want to know what will be the more probable, like a game theory, negotiation. What is his standing? What are his strengths? What are mine? So I don't have the problem. I'll be a bit more, give you a little bit more sense of what will be in the exam. I don't have that them prepared, but I have a tendency like combine problems, say, where you have, say, you need to find the stress concentrator and calculate a corrected stress, or maybe, we're ready to do one of that problems where you need to practice some statics and then go into applying the new stuff. So let's do problem 16, which talks about a lever, and problem, it's on 256 and shows a lever, it's loaded, and we need to calculate the second of the force to have equilibrium. It's a Belcring there, it's called. And then we need to calculate the shear stress upon the pin. So it's in single shear, not double shear. So in order to get the shear force, we have to find the reaction at the pin. So, and it's a lot of geometry there. So problem, begin with numbers. Problem 416. Then we have a pin, and there's the lever, and so we have a force here that goes at some angle from the horizontal, 30 degrees, and this is the input force F1, 3.6 kilonewtons. And then we have another force here that is slightly upwards, F2, which we don't know, but we can calculate it, and it's at 10 degrees. And then we know some geometry, so some distances. This is 30 millimeters. This is 25 millimeters. And then this is 10 millimeters. Measure from here to here. And then we have 40 millimeters this distance. Okay, and this is where I can make it like so. This is where the support is. So what do we need to do first? We need to the pin is well, we need to size the pin. It says so for the lever shown, the pin is made from beryllium copper. I don't know why they want beryllium copper, which is a brittle material. And the loads are repeated many times. Maybe we'll just switch to a more mundane material. Beryllium copper is used for like a non-magnetic spring. So allow me to switch to just, same 1020, mild steel. Okay. So let's use instead, I make that change. So, and tomorrow I'm going to just give you the material with its properties, part of the text of the problem, to make sure everybody picks the right value, at least not have divergences. Okay, so let's go with 1020 annealed. So 1020 annealed, SAE 1020 annealed. Why I changed it? Because I said that beryllium copper is brittle material, and the equations for shear are for, or the text even says if it's a brittle material, do more reading. And if we find beryllium copper now, which is together with the non-ferrous where titanium was, okay, so typical properties of stainless and non-ferrous. And I'm looking at the beryllium copper. And does it give the percent elongation? So soft, hard. Well, maybe they wanted the soft version. The hard version is only 4% elongation, and that means it's a brittle material. Yeah, the soft type is 20% elongation. But I switched to a SAE 1020 annealed. Okay, so we need to calculate this force, and once we know the two forces, then we can draw a free body. So some moments about the pin, and then we're going to draw a free body diagram for the entire bell crank, find reactions at the pin, and then their resultant, and then divide the area. Well, we need to calculate the diameter. So what's the diameter? D of the pin. Okay. So, and it says the stresses are repeated many times, right? And the loads are repeated many times. So we need to go to what the recommendations are when you have the loads that are repeated many times. But statics moment first. We're summing moments, stagnant. Let's call this O and A and B. So some moments about point O, we have equilibrium. We're assuming positive counterclockwise. So what is the moment of the top force, F1? We have, and it's causing a negative moment. So it'll be negative. The arm of the force, Well, we cannot get the arm, but we work with the horizontal vertical components. So we have, and both produce negative moments. So I have 33.6. We work with kilonewtons and millimeters just to get the moment, and then we can switch to Newton millimeters. So 3.6 times cosine of 30 degrees, it gets you the horizontal component. And the arm of the horizontal component, it's 30 millimeters. Okay, so I have the horizontal component. The vertical component likewise produce a negative moment according to this agreement, and the arm of the force is 40. So I have negative 3.6 kilonewtons times sine of 30 degrees, okay, times, is this value, are these values correct? Yeah, 30, 25, 40, 10. So negative sine of 30, and the arm of the vertical component is 40. My drawing is not quite this scale. Okay, so I took care of this force. This other force is causing the horizontal component F2 is causing a positive moment. So I have positive. It will be F2, the unknown, times sine of 10 degrees, and then times the arm of the horizontal component is 25. And then I have the vertical component of this force, and it causes a negative moment. So it will be F2, negative F2. I think that's a mistake. So I have the horizontal component goes with cosine. So cosine, or is a mistake, cosine of 10 degrees, and then I have times sine of 10 degrees, and then times sine, or at the times the arm of the vertical force, which is 10, and causes a negative moment. That's why the negative here. So times 10 equals 0. So I can solve for F2 now. Okay, so I'm just taking these two, move them, they become positive. So I have 3.6. Yeah, I can even pull it in front. So cosine of 30 degrees times 30 plus sine of 30 degrees times 40. Okay, and then divided by would be F2. Well, F2 would be cosine of 10 times 25, sine of 10 times 10. So cosine 10 times 25 plus sine of 10 degrees times 10. Okay? All right, so I started with the parentheses 30 cosine times 30 plus 30 sine times 40 equals times 3.6 equals over parentheses 10 cosine times 25 plus 10 sine times 10 close parentheses equals. Okay, so I've got 6.28 kilonewtons. This is what you've got. We can verify. We can sum. We can. Well, can we?
On the bottom, this time be negative, right?
Okay, let's go. Oh, yeah, this is negative. So yeah, that's a mistake. Need to start over. Thank you. You're paying attention. So I have the negative here that I missed. I pulled F2 in front. Cosine 25, 20, 10, 25. Yeah, need to go over again. So 30 cosine times 30 plus 30 sine times 40 equals times 3.6 equals over parentheses 10 cosine times 25 negative 10 sine times 10 close parentheses equals. Yes. So a bigger value, 7.23, I could say 4 kilonewtons. Kilonewtons. Okay, so we've got the forces, or the unknown force. I can even put it here, 7.234 kilonewton. And now we can we can do free body diagram to calculate the reaction. That's I'm removing the effect of the support, and I'm show and show the reaction. So it will be Rx and Ry. Tau is just going to be pi diameter of the pin square over 4 divided by Rx squared plus Ry squared square rooted. That's the formula that we're going to apply. So this is a lot of static, or more statics than the new stuff. Okay, so in order to get the reactions of the support, we can sum moments. I don't see a benefit. Let's sum forces in the y direction and x direction. Fx sum of forces in the x direction, sum of forces in the y direction equals 0. So for the x direction, I have, and this ended up being positive, so the orientation was unchanged. So I have, well, we can start from above below. So it will be 3.6 times cosine of 30 degrees, and then plus Rx plus going from and plus 7.234 times sine of cosine of 10 degrees equals 0. And in the vertical direction, I have, again, starting from top to bottom, will be negative 3.6 sine of 30 degrees. Okay, and then positive Ry, and then rather positive because it's up 7.234 times sine of 10 degrees equals 0. So what is Rx? It's going to be a negative value. Clearly, Rx is a negative value, this plus this with a minus in front. So 3.6 times 30 cosine plus 7.234 times 10 cosine equals, so negative, I said 10.242 kilonewtons. As for this other one, we cannot tell exactly. So this goes to the side, Ry. So this becomes positive. This is negative. So let's hope we don't do any mistakes. So 3.6 positive times 30 sine negative 7.234 times 10 sine equals, so I have 0.544 kilonewtons. Was it correct? My math slipped away. So 3.6 times 30 sine negative 7.234 times 10 sine equals. I've got a totally different number. You can tell that I haven't had lunch. So 3.6 times 30 sine negative 7.234 times 10 sine equal. Yes, and this is positive. So it means that Rx is actually this other way, and Ry is as shown. And we can calculate the reaction at the support. This was less. The reaction, they don't act simultaneously. You show either the components or the resultant. I represented the resultant. So R is going to be square root of what? 1024 2 squared plus 0.544 squared, square root. So 10.242 squared plus 0.544 squared equal, take the square root. So this is 10.242 256 kilonewtons. Okay, so we can calculate the design stress in shear. Actually, no, we don't have a diameter. If we could do an analysis and report a design factor and see if it's a satisfactory one. So this is equal to yield strength in tension for the material, and I said I'm using 1020 in yield. What was that? Never wrote down. I just kept on justifying my choice for that new material.